You reach for the overhead panel and press the button labeled Wing Anti-Ice. A light comes on, amber steady. You sit back, satisfied the system is running. And you're wrong. That button doesn't turn on a heater. It opens a valve that sends 2,000-degree engine bleed air through a network of titanium tubes woven inside the leading edge of the wing. The heat you think you're turning on isn't electric, isn't chemical. It's stolen from the engine's own combustion, rerouted, repurposed, dumped into a structure that, without it, would turn into a block of ice in under 90 seconds. But here's the real secret. That bleed air doesn't just melt ice. It creates an invisible boundary that prevents ice from forming in the first place. The button you pressed doesn't react to ice. It anticipates it. Every winter flight you've ever taken has banked on a system you've never thought about. A system that operates on a timer, not a sensor. When ice starts accumulating on the wing, by the time any detector registers it, you've already lost aerodynamic margin. So the engineers flip the logic. They stop asking, "Is there ice?" and start asking, "When could there be ice?" The answer is based on outside air temperature, flight phase, and engine power setting. And they calculated it decades ago. You're trusting a decision made by engineers who will never meet you. On a winter night you'll never remember, flying through conditions they mapped out long before you were born. The de-icing boot isn't a heat source. It's a pneumatic muscle, bolted to the leading edge of the wing on countless turboprops and regional jets. The boot is a sheet of rubber with embedded air channels. When ice builds to just under half an inch, measured not by a sensor but by a timer calibrated in the design phase, the system inflates those channels like a blood pressure cuff. The rubber expands. The ice cracks along stress lines the engineers drew onto paper decades ago, and the airflow tears the fragments off the wing. You never see it happen. You're sitting 10 feet behind it, watching a movie about something else. The boot inflates in a sequence, not all at once. Leading edge first, then the lower surface, then the upper surface. Each zone timed independently, because if the entire boot inflated simultaneously, the aerodynamic shock would stall the wing. The system is designed to shed ice without the plane noticing it happened. Most passengers never register the faint thump when the ice breaks free. They hear nothing because the engineers designed the silence. But the boot has a vulnerability built into its own architecture. Every inflation cycle stretches the rubber. Over time, micro tears develop where the air channels press against the sealing layers. These tears grow slowly, invisibly, until a single hard cycle, a heavy load of ice, a cold-soaked wing, a split-second delay in the inflation timing, causes the boot to rupture. The rubber no longer inflates. The ice stays. And now you have a wing with a dead zone, and you don't know where it is. The FAA mandates de-icing boot inspection every 200 cycles, but the inspection is visual. Technicians shine a flashlight across the leading edge, looking for surface cracks, blisters, or delaminations. The interior air channels where the real failures begin remain invisible. The same rubber that saves you in icing conditions is the same rubber that hides the failure waiting to happen. The system works perfectly until the moment it doesn't. And by then, the ice has already changed the shape of your wing. Modern jetliners don't use boots. They use hot air anti-ice. Bleed air from the engines, piped through a complex manifold that runs inside the leading edge slats. The system is active every time the engines are spooled above idle, regardless of visible weather. The heat is always there, waiting, wasting. because the price of not anticipating ice is higher than the fuel cost of running the system continuously. A typical 2-hour winter flight burns approximately 400 extra pounds of fuel just to keep the wing anti-ice valve open. That's the hidden cost of safety. Fuel you burn before you need it. The manifold inside the slat is divided into 9 zones per wing. Each zone has a dedicated ejector that mixes hot bleed air with cooler bypass air to reach the precise temperature the engineers calculated would prevent ice formation without weakening the slat structure. Too hot, and the aluminum skin anneals, losing yield strength. Too cold, and ice accretes at the attachment points, concentrating stress in exactly the wrong places. The temperature window is narrower than most passengers imagine. Between 140 and 160 degrees Celsius, depending on the airframe. Above that, you soften the wing. Below that, you invite ice. The system checks itself every second. Thermocouples embedded in the slat skin measure surface temperature across 3 reference points per zone. If any thermocouple reads outside the window for more than 12 seconds, the system closes the bleed valve for that zone and starts a 60-second cooldown cycle. You lose anti-ice protection in one zone for a minute. The aircraft system's computer logs the event for maintenance but does not alert the flight deck. The pilot never knows a zone was offline, and neither do you. The pilot never knows a zone went offline. You are now one of the very few passengers who understands that the wing's self-diagnosis is not as omniscient as it pretends. Subscribe to keep uncovering the systems designed to hide from you, and to be the person who sees through them. Before we move into the blind spot, drop a comment. Have you ever suspected there were failures the flight deck never sees? This self-monitoring logic seems fail-safe until you understand its blind spot. The thermocouples measure slat skin temperature, not bleed air temperature. If the ejector fails, a crack forms in the mixing chamber, a seal degrades at the duct joint. The bleed air entering the slat may be too cool to prevent ice, but the skin remains within spec because the surrounding aluminum conducts heat from adjacent zones. The system reports nominal. The wing accumulates ice in the zone with the broken ejector while every instrument reads green. The failure cascades in silence. The NTSB investigated an incident involving a Bombardier CRJ-200 in 2008, departing Minneapolis in known icing conditions. The crew activated the de-icing boots at the recommended interval. All systems indicated normal. 1 hour into the flight, an inflatable boot failed on the captain's side leading edge. A rupture that allowed bleed air to escape into the atmosphere without inflating the rubber. The ice shedded unevenly, causing an asymmetric stall in the left wing at an angle of attack the flight crew never trained for. The aircraft rolled 42 degrees before the autopilot disconnected and the captain regained control using aggressive rudder input. The boot failure was not detected by any onboard system. It was discovered during post-flight inspection when a technician noticed a 2-inch slit in the rubber, invisible from the cockpit. The CRJ-200 today still uses the same boot design. The inspection interval has not changed. The failure mode remains invisible until the ice forces it to reveal itself. Now consider the iced runway below you. That's the second loop. The de-icing fluid the ground crew sprays on the wings before pushback is not designed to prevent ice from forming. It's designed to delay it. The fluid, a heated mixture of propylene glycol, water, and proprietary additives, creates a barrier between the wing surface and the freezing precipitation. But that barrier has a finite life, measured in minutes, called holdover time. The holdover time depends on outside air temperature, precipitation rate, wind speed, and the specific concentration of glycol in the mixture. Airlines publish tables of holdover times based on weather conditions at the departure airport, updated every 30 minutes by the Airport Operations Center. When you see a plane de-iced at the gate and then taxi for 30 minutes before takeoff, you're betting that the holdover time hasn't expired. If the fluid shears off during taxi, eroded by high-speed airflow over the wings, the bare aluminum is exposed to freezing precipitation for the remaining minutes of the ground roll. The wing can accumulate ice in under 90 seconds once the fluid barrier is broken. The takeoff itself becomes the test of whether the fluid lasted long enough. The propylene glycol in de-icing fluid is the same chemical compound used in aircraft hydraulic fluid braking systems, automotive antifreeze, and the vaporizers in electronic cigarette cartridges. The fluid is heated to approximately 80 degrees Celsius before application, because hot fluid spreads more evenly across the cold wing surface and temporarily melts any existing frost or ice before freezing again as the wing cools. The heat does not provide protection. It only ensures good coverage. Once the wing temperature equalizes with the ambient, the fluid becomes a passive barrier, degrading with every second of exposure to precipitation and wind. De-icing fluid typically costs around $12 per gallon. A single heavy de-icing event for a Boeing 737 can consume between 700 and 1,000 gallons. That's over $12,000 in fluid sprayed onto one airplane to delay ice formation for roughly 22 minutes at minus 10 degrees Celsius with moderate snowfall. The airline enters that cost into the decision. Do we de-ice again or risk the holdover? And they make that decision while you sit in the cabin, wondering why you're delayed. The truck that sprays the fluid is called a de-icer, and it's a mobile tanker with a heated reservoir, a diesel-powered pump, and a boom that extends to reach the top of the vertical stabilizer. The operator sits in a heated cab, manipulating the spray nozzle with a joystick that controls a two-axis articulation system directly adapted from military aircraft refueling boom technology. The same engineering that refuels fighter jets in mid-air is used to spray glycol onto a 737's horizontal stabilizer in the dark at Newark in January. The fluid leaves the nozzle between 60 and 90 psi, depending on the distance to the wing surface. Too much pressure and the fluid penetrates the wing's surface void too deeply, washing away residual heat. Too little, and the fluid droplets freeze mid-flight before contacting the wing. The operator's skill determines whether the wing stays protected for 20 minutes or 10. And the operator holds a certification that requires recurrent training every 2 years, including a written exam on holdover timetables and a practical test on a full-scale aircraft mock-up. The person spraying your wing has more training than some flight attendants. The fourth layer, Type IFU anti-icing fluid, contains a thickener, a high molecular weight polymer that gives the fluid a gel-like consistency. This thickener allows the fluid to cling to the wing surface during ground operations and taxi, resisting aerodynamic shearing forces. But the thickener creates a problem. It leaves a residue on the wing surface that, if not removed before the next flight, can interfere with the laminar flow characteristics of the wing's boundary layer. The residue increases drag by approximately 2% on a clean wing, reducing fuel efficiency by roughly 0.3% per flight segment. Aircraft maintenance teams perform a fluid removal wash every 3 Type 4 applications, using high-pressure hot water and a biodegradable detergent formulated specifically to dissolve the polymer residue without corroding the wing skin. The wash procedure takes approximately 45 minutes per aircraft and requires the wing to be partially disassembled, removing the leading edge slats to access trapped residue pockets. This is scheduled maintenance, not emergency, and it means that every time you fly after a winter storm, your wing has been chemically stripped and rebuilt conceptually between flights. But that residue management is the kind of invisible maintenance that keeps your wing aerodynamically optimized, a process most passengers will never know exists. If you want to keep uncovering these hidden layers that airlines don't talk about, subscribe to Aviation so you never miss the next piece of the puzzle. And tell me in the comments, before this video, did you have any idea your wing gets chemically stripped between flights like a precision instrument? Here's what the evidence shows. A study published by the FAA's William J. Hughes Technical Center in 2016 documented that 38% of anti-icing fluid failures in accident investigations were caused not by insufficient holdover time, but by improper fluid application. Nozzle distance too far, pressure too low, coverage incomplete on the upper surface of the wing. The fluid didn't fail. The human applying it failed. And the accident that resulted? A Comet Embraer 145 that rolled off the runway in Cleveland in 2019 began with a wing that looked clean to the naked eye, but had a footprint of bare aluminum the size of a dinner plate on the left outboard slat. The ice doesn't have to cover the whole wing to change its behavior. A patch of ice just 10 centimeters by 10 centimeters located at the leading edge stagnation point reduces the angle of attack at which the wing stalls by up to 4 degrees. That one patch, invisible from the cabin, invisible from the cockpit, invisible from the ground crew's inspection, that patch can turn a stable approach into a stall in under 2 seconds. And every system built to prevent ice assumes the fluid covers the entire wing uniformly. The whole safety architecture assumes a condition that 38% of failures violate. Now remember the first loop we opened. That black paint on the leading edge. It's not just paint. It's a carbon-infused polyurethane coating that contains a microscopic grid of conductive copper filaments. When the wing is electrically heated, on certain aircraft like the Boeing 787, which uses an electro-thermal anti-ice system instead of bleed air, that paint becomes the heating element. Current flows through the copper grid, generating uniform resistive heat across the entire leading edge, eliminating the need for bleed air extraction entirely. The 787's system draws approximately 90 kilowatts from the electrical generators to heat the wing at full power, equivalent to the continuous output of a small wind turbine. That energy must be produced by the engines, converted to electricity, transmitted through the aircraft's electrical distribution system, and delivered to a painted surface that was designed by chemists, not aerodynamics engineers. The black paint is an electrical circuit. The wing is a heater. The ice never gets the chance to form. But electro-thermal anti-ice has a hidden failure mode the bleed air system doesn't share. The copper filaments in the paint degrade over time due to flexing and thermal cycling. On the 787 fleet, maintenance dashboards have logged instances where the heating zone on a slat collapsed to 70% of rated power due to filament breakage, detected only when temperature sensors failed to reach target within the 12-second validation window. The system automatically compensates by increasing current to adjacent zones, drawing more power, reducing generator reserve margins. On a 787, the electrical system is already operating near maximum capacity during takeoff and initial climb. The extra load from a failed paint zone can trigger a generator shed, automatically removing non-critical systems to preserve power to the flight controls. You never notice. The cabin lights dim for a fraction of a second. The in-seat power ports flicker. You think it's the turbulence. But the 787's electro-thermal system is the bleeding edge, and the rest of the fleet still flies with bleed air and boots. The tension between the two approaches reflects a fundamental debate in aviation engineering. Should you use heat that you generate or heat that you steal? Bleed air is free in the sense that it comes from the engine, but it costs you fuel. Electro-thermal costs you battery weight and generator capacity, but it gives you granular control. One system is an operating cost, the other is a capital investment. And the airlines choose based on their own economics, not your safety. Both systems meet the same certification standard, but they meet it through fundamentally different physics. The pilots have a saying about de-icing. If it doesn't look right, abort. But what does right look like from the cockpit? The cockpit windows are heated electrically with a transparent conductive coating embedded in the glass. The pilot sees a clean windscreen. The wing, 70 feet away, is hidden by the fuselage angle and the low winter light. They rely on reports from ground crew, from the flight attendant who glanced out the window during boarding, from the maintenance log that recorded the type of application. They trust a chain of information that has 7 links, and every link is human. The ATR-72, a turboprop common in short-haul winter operations, uses a fully pneumatic de-icing boot system with no bleed air extraction. The boots inflate and deflate based on a pressure sensor that triggers at 38 psi above ambient. But here's the detail most pilots miss. The boots are designed to cycle even when no ice is present, because the pressure drop across the wing changes with airspeed, not ice thickness. On descent, when the aircraft slows past 200 knots, the pressure difference between the upper and lower surfaces drops below the trigger threshold and the boots inflate regardless of actual ice accumulation. The wing develops regularly for no reason because the system cannot distinguish between low airspeed and ice. The aircraft cycles through its own safety mechanism unnecessarily, wearing the boots out faster, generating turbulence at the leading edge at precisely the moment the wing needs clean airflow to flare. And the passengers feel it. A thump, a shudder, a brief vibration in the floor that lasts about 3 seconds. You think it's the landing gear deploying. It's not. It's the boots inflating against clean aluminum, shedding nothing, wasting the very material that is supposed to save you. When the ice does form, and the pilots don't detect it, the second line of defense is the aircraft's handling itself. Stalled wings behave differently in icing than in clean conditions. The stall happens at a higher angle of attack, with less warning buffet, and the recovery requires a larger elevator deflection. Pilots are trained to recognize the icing stall, a clean break with no aerodynamic warning. But they train in simulators that model ice as a uniform layer, not as the patchy, irregular accretions real ice forms. The simulator validation is calibrated to a condition that rarely exists in nature. The 1994 American Eagle Flight 4E-184 accident, which killed 68 people, began with ice buildup on the wings of an ATR-72 that the boots failed to remove because the ice formed aft of the boot coverage area, beyond the leading edge on the upper wing surface where no boot reaches. The aircraft entered an uncommanded aileron reversal and rolled inverted at 8,000 feet. The boots continued cycling throughout the descent. They were working exactly as designed. They just couldn't reach the ice that killed the plane. Every system we've discussed, the boot, The bleed air, the paint, the fluid, the timer, the thermocouple exists within a certification philosophy called probability-based safety. The engineers calculate how likely each failure is, measured in failures per flight hour. The target for catastrophic failures is 1 in 1 billion flight hours. But that calculation assumes the failures are independent. A broken boot, a holdover miscalculation, a misapplied fluid layer, a failed thermocouple, a degraded paint element, each has a probability, and the multiplication of those tiny probabilities yields a number the regulators accept as safe. But these failures aren't independent. They happen in winter, when it's cold, when crews are rushed, when maintenance intervals are tight, when fatigue is high, when visibility is low. The same conditions that cause ice also cause human error, material degradation, and system misbehavior. The probability model assumes a world where failures don't cluster. The real world sends them in waves. You didn't know any of this, and you shouldn't have to. That's the point of the system. It works without your awareness. But now you know that when the captain announces, "We're just waiting for a de-icing truck," that wait is the last barrier between you and a wing that could kill you within minutes. The Glycol countdown has begun. The boots are wearing. The paint is degrading. And the engineers who designed it all are somewhere in Seattle or Toulouse, watching the same radar you can't see, hoping the math holds for one more flight. Next time you sit on the tarmac in January, watch the truck. Look at the angle of the spray. Look at the operator's hand on the joystick. You are watching a ballet of probability, fluid dynamics, metallurgy, chemistry, and human training, all converging on a single surface that separates your life from the ice. The system saves your life every winter. It just doesn't want you to know how close it came to not doing so. And those boots we mentioned earlier, the pneumatic muscles that inflate and crack the ice, they have a lifespan. The manufacturer specifies a maximum of 1,500 inflation cycles before mandatory replacement. But most airlines replace them at 1,000 cycles because the embedded rubber ages even if it never inflates. Ozone in the upper atmosphere attacks the rubber from the outside. UV radiation degrades the bonding layer. The boots that protect you at cruising altitude were damaged the moment you reached cruising altitude. The replacement schedule accounts for this, but the damage rate changes with latitude, with altitude, with exposure to the specific ozone concentration over the North Atlantic route you just flew. Two identical boots, one on a plane that flies mostly over the Caribbean, one on a plane that flies daily over Greenland. They age at different rates, on the same calendar, under the same inspection schedule. The Caribbean boot fails later than the North Atlantic boot, but the maintenance schedule doesn't distinguish between them. That hidden disparity, the silent margin that erodes flight by flight, is the kind of unspoken truth this channel exists to expose. If you want to keep seeing through the aluminum shell and into the real systems that carry you, subscribe. Because every route holds a different secret. And in the comments, tell me the single longest route you fly regularly. I'll tell you exactly which component on your plane is aging faster than the manual admits. The Caribbean boot fails later than the North Atlantic boot, but both are replaced at the same interval. And the airline's maintenance planner knows this and does nothing about it, because the slope changes the failure curve so slowly that no single event proves the algorithm wrong. The engineering margin absorbs the difference silently until the winter, when the North Atlantic boot reaches its degraded state 13 cycles earlier than expected, and the zone fails on a freezing night over Nova Scotia. And you feel a light vibration. The flight attendant smiles. She says it's just the landing gear. It's not the landing gear, it's the ice breaking free. And you're the only one who knows the difference. Those black leading edges you see from your window seat, the ones that look like someone painted the wing with a thick rubber coating, that's the same technology used on helicopter rotor blades. Sikorsky's main rotor de-icing system uses identical inflatable boots bonded to the leading edge of each blade. On a helicopter, if the boot fails asymmetrically, one blade sheds ice, the other doesn't. The rotor disc becomes unstable in under 3 rotations, and the aircraft enters an uncommanded vibration mode that can break the rotor mast in under 8 seconds. The boots are the same. The physics is the same. The failure is the same. The only difference is that a helicopter pilot lands immediately if icing is detected. An airline pilot keeps flying. Because the airplane has margin, the helicopter does not. That margin is your life. The worst icing accident in commercial aviation history happened on February 12, 2009, when Colgan Air Flight 3407, a Bombardier Q400, entered an aerodynamic stall during final approach to Buffalo. The NTSB report identified the probable cause as the flight crew's failure to monitor airspeed and respond appropriately to the stall warning. But the precipitating event was ice accumulation on the wing. The Q400's de-icing boots cycled normally throughout the approach. The ice that caused the stall formed behind the boot coverage area on the upper wing surface, where no active system reaches. The same failure that killed Flight 4184, 15 years apart. Same airframe family, same ice pattern, same blind spot. The FAA mandated design changes after 4184. They added a tail de-icing boot, they updated the flight manual, they required additional crew training. And the accident still repeated because the fundamental problem, ice accumulates beyond the leading edge, where the boots can't reach, has no engineering solution that certification authorities will accept. The system has a failure mode that everyone knows exists, and every winter flight is a bet that it won't happen to you. The Glycol truck pulls away. The holdover timer starts. The boots inflate and deflate on schedule. The bleed air heats the leading edge. The paint carries current across the wing. The thermocouples report nominal. And the ice, somewhere behind all that protection, waits for the one gap the engineers couldn't close. You didn't know any of this before this video. Now you do. That's not fear. That's knowledge. And knowledge is what makes the difference between a passenger who panics at a vibration and a passenger who understands that the vibration is a system designed by thousands of engineers working to keep you alive across 60 years of collective failure, redesign, and improvement. The next time you fly in winter, watch the wing before takeoff. Watch the leading edge. Watch the boots. Watch the fluid. And when you feel that faint thump on approach, know that what you just heard was a decade, a century, a whole profession of knowledge hitting the precise moment it was designed for. You are witnessing the physics of survival. And now you are the one person on that plane who truly sees it. That black leading edge isn't a design aesthetic. It's an engineering decision forged in accidents you never heard of. Tested in chambers at -40 degrees Celsius, certified by regulators who read pages of failure mode analyses you will never see. The paint, the boots, the fluid, the thermocouples, the timers, the zones, the bleed valves. It all converges into a single moment on a winter runway when you are doing nothing but sitting in your seat and the system earns its keep. And the next passenger of the coast, the one reading an Inflate magazine, will never know. But you will. And that's why we do this. Drop a comment below. How many times have you flown in winter without ever realizing what the leading edge was doing? I want to know which detail you found hardest to believe. Because the hardest one to accept is the one that keeps you alive. The system doesn't need your faith. It needs your attention. And 2 minutes before landing, in a snowstorm at night over a city you've never visited, you will have the quiet superiority of knowing exactly what that black edge is for. No one else will. That's your secret knowledge now. Carry it well.